Hello. In this video, I am going to introduce you to the concept of future value and work through some different cases as examples of how you use future value. I'm going to apologize in advance. This may be a little bit of a lengthy video. I'm going to try and be concise as I go through it, but there are several cases to cover, and I want to make sure that we get through all of those. So, topics, we're going to cover the basic idea behind future value, and then we're going to go through these 6 cases. So, future value basics. The entire concept of future value is based on the idea that you have a choice between either having money today or at some point defined in over time, or waiting and getting that money later. And so usually people would require that if they're going to get the money later, they're going to want to have more money than if they get it now or they get it sooner. And so the first question is why? Well, if you think about it for your own purposes, the sort of opportunity costs associated with not having money now, and so then having to wait might be, number one, it's just an inconvenience. If you had the money now, you could enjoy whatever you're going to do with it now, and so that element of it, if you will, impacts your willingness to give the money up and what you would want in return for it. You also have an understanding that when people give money up in the present and have to wait to receive it in the future, we have this expectation that you should earn interest on it. Think of it like it's an investment, and if I'm going to have to wait to get it, then I'm going to need more of it to compensate me for that delay. So I expect it to grow. And so if somebody says to you, hey, can I pay you later, maybe in a business, then you may think about, well, let's see, if I had that money now and I didn't do anything else with it, I could put it into an investment that earns a certain amount of interest. And so by waiting, I'm not getting that interest. So in return for that, I'm going to tell you that if you pay me later, you at least need to cover that cost of that interest. There are sometimes some other considerations that will go into why you might prefer it now. One might be inflation. If you can use the money to purchase things now, they may be cheaper than if you have to wait and purchase them in the future. And so you'll want to make sure that whatever you do makes sense in that context. And then there's also the notion of certainty of payment. If I get the money now, I have it. I know I have it. I don't have to worry that I'm not going to get it. When I tell you you don't have to pay me now, you'll pay me later, I have that entire period of time where I hope that you pay me, but I'm not sure that you pay me, and there's some possibility that something goes wrong and you aren't going to be able to pay me. And so that poses a risk to me that I may not get my money back. And so those are the kinds of things that cause us to want more money in the future. In this case, that would be compensating you for all of the stress and the risk and the uncertainty that goes with not knowing for sure you're going to get paid. Generally, from that thought process, individuals will develop in their mind some fair rate of interest, is what we call it. So some fair compensation that will cause you to be willing to delay receiving it today and instead get it tomorrow or a year from now or however far that is. And so you have some notion of how much you need to get in return for that. Now, sometimes that's called an interest rate, sometimes that's called a rate of return, sometimes that's called a compounding rate, but it's some rate. And that rate can be just a flat amount. I need $500 more. It can be I need 3% more. It can be I need this much in the future, and then you can solve for what the implied rate of that is. there's again a lot of different theory that might go into your process for figuring out what that rate is. This particular topic is not about how that rate might be determined. It's really about, once you have that rate, what you can do with it. So we're not going to dwell right now on how you figure out what the rate is. So let's now jump into our cases. We're going to start with a simple case. The very first case is, imagine that I have an amount of money today, $100, and I am, instead of spending it today, I'm going to invest it. And I have been told that the fair rate, and it's a rate that I am fine with, for investing it for 1 year is going to be 6%, and that I'm going to get that money, the 6% of my $100, I'm going to receive it at the end of the year. So, question is, this is what the future value question is. How much money will I have in the future? In this case, the future being 1 year from now. And I think most of us can do that math. We're going to start out with $100. We're going to earn 6% on that, so $6 by waiting a year to use it. And so at the end, we're going to get our $100 back plus $106. And so the future value of the $100 invested under these terms for a year is $106. Take a deep breath. You've now done future value. That's all it is. There's nothing complicated about this. There's some more complex cases, but in essence, they all are just examples of this. So, how can you go about mathematically doing what we just described? Well, let's see. We got future value. It's equal to the $100, right? And then it's equal to $100 times 6%. That's the $6. And you add those together and you get $106. And so algebraically, because we got the two hundreds in there, we can take them to the outside. This becomes 100 times 1 plus 6%. It's $106. Still makes sense. So 1.06 times 100, 106. And this formula, we can do what we call generalizing it. And generalizing it is to turn it into variables so that we can plug in different amounts. And so we would generalize it by first saying, oh, the $100, we'll call that A. And I'm just picking that. Somebody else might call it something else. A stands for the amount. So this is the amount initially invested. So we're going to call that A. And it's times 1 plus R, where R is the interest rate. So if I do A times 1 plus R, I could plug any number into that formula, any number for A and any number for R, and I could solve for what the 1 year investment would be worth. Now let's take this a little bit further, and let's just say that instead of investing it for 1 year, we're going to invest it for 2 years, or maybe more than 2 years. So we're going to go through the same process. We start with $100. The end of year one, we earn interest of 6% on our $100. That's $6. So at the end of year one, we have $106. Now here's where it gets a little bit different. In year two, we now earn 6% on the $106, not the original 100. So now we earn $6.36 for the second year. So at the end of the second year, we have the $100 plus the $6 that we earned, plus another $6.36. That's $112.36. So that's how much we have at the end of the second year. So the question becomes, why did we earn more interest in year two than in year one? The answer to that is we had more money invested at the beginning of year two because we had the initial investment of $100 plus the interest that we earned in year one. So that second year, we earned interest on both the initial value and the interest earned, meaning we earned interest on our interest. And when you earn interest on your interest, we refer to that in financial theory as compounding. So you've compounded your interest. So that's a very powerful concept, particularly investing. So we'll probably want to explore that here in just a minute. But first, let's go back and think about mathematically how we could simplify what you just did. So you got the $100, and then at the end of year one, you got $100 times 6%. And then you've got $100 plus $100 times 6%, so $106 times 6%. This is your year 2 amount. So that becomes $100 times 1 plus 6%, and then that whole amount times 1 plus 6%. Okay? And if we were to simplify that just by recognizing that if I take 1.6% times 1, or 1.06 times 1.06, we can simplify that into 1.06 squared. That's just what squaring means. Then we've now simplified it into this. Now, again, the goal would be to generalize this. And so here we have the 2-year amount is equal to the initial amount times 1 plus the rate squared. So we've now generalized for this investment an easy way where we could plug in an amount and a rate in, and we could get the future value of it. So what I'm going to have at the end of 2 years very easily. Now, that's one case just for 2 years. What about if we did this for 3 years? Again, we could do all the same things through year 2. At the end of year 3, or at year 3, we're going to earn interest on the 112.36, and so we're going to earn 6.7416. So that's 6% of 112.36. Okay, and so now we're going to add up the 100 plus the 6 plus the 636 plus the 6.7416. By the end of year 3, it should say, sorry about that, we're going to wind up with $119.10 roughly. So again, have gone through a similar process. Didn't really change our method at all, but hopefully that tells us something about what happens as we go adding years to this. So again, mathematically, this really is the 100 times 1 plus 6% times 1 plus 6% times 1 plus 6%. Simplifies to 1 plus 6% to the third power. If we notice that this third power, which we call the exponent, is equal to the number of years into the future we're investing the money, then we can generalize this formula to just say that the future value is the amount times 1 plus the interest rate raised to however many years it's going to be out there. So that's just a simple mathematical way of going through that process of building out what you have each year and what you reinvest, what's there to be reinvested at the interest rate and compounded each year. So the key to this is really to understand this power of compounding. It's kind of hard to grasp with the simple examples where you go through a year or 2 or 3 years because it just doesn't seem like a whole lot of money. Doesn't seem like it makes much of a difference. I mean, in our example, after 3 years, we wound up with an extra $1. It just doesn't seem like it's worth all of that. But the thing about compounding is that the further out in time you go, the more of a difference it makes. And so consider that I invest $100 at 6% for 10 years. If I didn't earn interest on interest, then I'd just get $6 each year for 10 years. I'd make $60. I'd have $160. Big whoop. But with compounding, I get $179. So I've made an extra $19. That's starting to be meaningful. That's like a third more than I thought I would have got without the compounding. Now, what happens if you go out to 20 years? So at 20 years, it's 6%. I'd get $6 a year, so I'd have $120. Add that to my $100, it'd be $220. So that would be if there were no compounding, I'd have $220. But instead, using our formula, which you should try and solve for yourself, we get $320.71. So we've gone from 200 to 320. We're now getting close to almost doubling the amount of interest that we earn. And more importantly, with this compounding and the overall investment, we've tripled our $100 by the end of 20 years. So let's see, you're 20 years old, let's just say, and you're going to retire at 65. So let's think about what happens over 45 years. At the end of 45 years, your $100 has grown to $1,376.46. That's pretty good growth. Again, we could sit down and kind of figure out that, oh, if I had gotten $6 a year over that period for 40 years, then that would be 6 times 40 would be 270. So, pretty much $1,000 of this $1,300 value is now interest on interest. It's the compounding. Otherwise, you would not have wound up with that much money. So now the other thing to think about is, well, what if instead of being at 6%, we were investing at 8%? How would that impact things? Again, for this example of going out 45 years, you went from $1,376 to almost $3,200 just by moving the interest rate a little bit. And the reason is the combination of time and the interest rate is really what is creating this compounding benefit. So I want you guys to know the math for doing this, but I also want to give you sort of a basic rule for in your head thinking about this. There's a rule called the Rule of 72. And basically what it does is combine, in a simple sense, for kind of normal levels of interest rates, this concept of the importance of time and the importance of interest rate to give you some idea of how it impacts the value of your investment. And what the rule does is it states that you can estimate how long it will take you to double your investment by taking 72 and dividing it by your interest rate. So for example, let's say that you have an interest rate of 6%. You divide 72 by 6%, you get 12 years. And so ideally, if you invested some money at 6%, then by 10 years or 12 years out, it should have pretty much doubled. So you can check that using the formulas we used before and see that at the end of 12 years, your $100 would be worth about $201.22. So sure enough, about doubled. So it's not perfect, it's not exact, it's not how I want you to solve things in class, but it's a nice little in your head sort of thing for thinking about if you've got investments that you're going to put out for a long period of time, how you can sort of quickly approximate their value. Next thing that we're going to talk about is something called subannual compounding. Subannual compounding, this is a term that I use. I've not seen it used anywhere else, but I like trying to sort of give you something that is a label that we can all understand. And so subannual compounding is simply the idea that instead of you getting your interest payments once a year at the end of each year, you're going to get them at increments of time that are less than a year. So subannual, shorter than a year. And so in those, there are cases, for example, with banks and so forth, where let's say that whether they're paying you or they're charging you, but they would basically say, we're going to compound this interest rate quarterly, as an example. And so what that means is that instead of you just having an interest amount once at the end of the year, you're going to get an interest charge each quarter. And now you have to think about that if you don't pay that interest, you're going to get charged interest on interest. Or if you're receiving the interest, it's now in an account, and so by the next quarter, interest is going to be based on having that amount in the account as well. This works very similar to the the formulas that we've already done before. Really, the only difference here is that you have to solve for a number of periods instead of a number of years, and you have to figure out a period rate instead of an annual rate. And so here's kind of the simple example. Assume I invest for 1 year at 6%, but the interest payments are made at the end of each quarter. So 4 times a year. That means the number of compounding periods in that 1 year is actually 4 periods. 6% interest rate that I gave you is what we refer to as the stated annual interest rate, or the SAIR, or SAIR. Also, it goes by a lot of different names. Sometimes it's called the annual percentage rate, or APR. Sometimes it's called the nominal rate. Sometimes it's just called the stated rate. All of those mean the same thing, which is it's a number that basically you can use as the basis for calculating what you're going to earn. Here in a second, I will contrast that to what I believe is a more informative rate called the effective rate of interest. So by convention, the interest rate earned each quarter, if somebody tells you that it's 6% compounded quarterly, then what they're saying is that your periodic rate is each quarter you're going to get 1/4 of 6%, right? Because basically the percentage divided by the number of quarters. So you're going to earn 1.5% each quarter. So given that, you can now figure out what you would have at the end of the year. So now remember that you're thinking in terms of periods instead of years. You're getting an amount. Again, that's your initial 100. The rate is now the periodic interest rate, so it's 1.5%. Number of periods is in instead of numbers of years. And so it would be 100 times 1 plus 1.5% raised to the 4th power. So if we did that, we would wind up with $106.14. Now, I don't know if you remember the prior example, but we only had $106. So the extra 14 cents is the interest on interest that we earned by compounding this quarterly instead of annually. Further, we actually wind up at the end of the period with $106.14, which means that our $100 over the year truly grew by 6.14%. And this is what we call the effective interest rate. And so rather than being a stated rate that you then divide by things, the effective interest rate is simply the amount you had at the end of the year divided by the amount you started at the beginning of the year. The value of talking in terms of effective rates and effective interest rates is that with that information, I don't really need to know things like how frequently it's compounded or whatever else in order to know what I can expect as my return. I just know that my effective rate becomes, I expect by the end of the year, of each year, I'll have 6.14% more than I had at the beginning. Whereas if you aren't talking in terms of an effective interest rate, you do need to clarify how frequently the compounding is. So let's just use the subannual compounding slightly differently and use it for multiple periods instead of, or years instead of the one. So in this case, let's say that we're going to invest for 4 years at 6%, interest payments made each quarter. That means we have 16 periods. So you see that here. So 100 times 1.115, so that's just the 6% divided by 4. Raised to the 16th power, 126.90. So I'm going to leave that for you guys to sort of solve for yourself, and check my work. But you can see that basically the formula looks the same. We've just redefined now and said that R is the periodic rate and N is the number of periods. So this is a generalization of the original formula that only spoke in terms of an annual rate and number of years. If we just simplify it down to periods, then you're using the same formula over and over for future value. Next instance we'll talk about is what's called superannual compounding. So sometimes you don't receive a payment every year. There's more than a year gap in between. And so I call it annual compounding because it's more than a year. And so super is the prefix for more than. So again, the compounding works very similar to in the subannual compounding example. but you have to solve for your periods and your interest rate based on a period that's longer than a year now. Just need to remember that in this case, the number of compounding periods is less than the number of years, and that the rate that you're going to compound at is more than the stated rate. So, again, simple kind of case. Consider a $100 investment that pays a stated rate of 6%, but only pays the investment once every 2 years. You will be invested for 10 years. So, number of payments per period is years divided by the number of payments, right? Or the length of the payment period. And so in this case, 10 divided by 2, there's only 5 payments. All right? So over the course of the 10 years, you're going to get 5 payments, one at the end of year 2, 4, 6, 8, and 10. And so at the end of year 10, you're going to get your payment of your interest, plus you're going to get back your $100. All right. Now, the periodic interest on this is equal to the interest paid over a 2-year period. So in our case, we would just say that it is the compound rate. If it's 1.6%, we're going to raise it to however many years it is, and then subtract 1 from it. So it's 1.1236. Then you subtract the 1 because it's not 112%. It's just that you need that for the compounding. And so it's 12.36%. So you're going to earn 12.36% each 2-year period. Now that you've done that, you can basically plug it into the same formula we had before. It's 100 times 1 plus 12.36, which is the 2-year, so the periodic interest rate for a 2-year period, raised to the 5th because there's 5 2-year periods in the 10 years. Gives you 179.08. I'll let you check my work on that. Just want to make the point to you, we're using the same formula over and over again. We're just simplifying, we just have to solve for what's the right period and what's the rate that goes to that period. Got one last example here that we're going to talk about that is sort of this one payment type example. This is called continuous compounding. With continuous compounding, imagine that you could take the year. So think of this as a special case of the subannual compounding. You can take the year and you can keep slicing it into smaller units. So you can go from a quarter to a month to a day to an hour. You could basically keep slicing it up and saying we're going to pay interest this frequently, once an hour, once a minute, once a second. At some point, the sort of limit of that, the smallest period that you can slice it into is an instant. And so we would call that instantaneous payments, and that you would be compounding instantaneously. We use the term continuous compounding to mean just imagine what would happen if you earned interest every instant. When it gets to this point, you could go out and try to do the sort of period process and number of periods that we did before, but we don't know how long an instant is. And so rather than do that and just wonder whether we got exactly what we needed, smart mathematicians using calculus have figured out that when you compound continuously, the factor, so the rate that you're going to be multiplying by your amount by, just reduces down to something called e to the rn plus 1. That probably looks like nothing to you. Here's e is what's called a mathematical constant. It has a value it's about 2.78128. It's something that's used a lot, not just in finance, but in a number of sciences and so forth. And it just turns out that works. R is the stated interest rate in this case. That's the power, if you will, of this approach, is that it allows you to use the stated interest rate without having to do anything else to it. And N is the number of years. We don't have to think in terms of number of periods anymore, because that's all handled through this E factor. And so all we have to do is that. Now, what we're doing there is taking stated rate times number of years, multiplying them together, and that becomes what we call the exponent. So you raise E, this value of 2.78, to whatever power this is, and that's going to give you a number, and that number's always going to be greater than 1, provided that we're talking about a positive interest rate. And so when that happens, you have to subtract 1 off of it to get sort of your effective rate. So let's just use an example. Let's say that I have a 6% investment over a year, right? But it's going to be continuously compounded. So I would do E to the 6%, which is my rate, times 1 for 1 year, minus 1. So that's the constant raised to the 6%, basically, minus 1. And that solves out to 1.061837 minus 1, or 6.1837%. So if we were to compound continuously, would grow at 6.1837%. Okay. Now, if you want to do this for 2 years, you go through the same process, but you have a 2 in here instead of a 1. Gets 1.1275. You could just keep doing this for as many years out to get that value. This is not the amount of money you're going to have. This is what I call the compounding factor. It's what you're going to multiply your initial investment by in order to know what you're going to wind up with at the end. So to get future value, you would take your initial investment, $100, times your compounding factor, and you get $112.75 in the example for 2 years. All right. I have one last case, and then we're done. And again, I apologize. This is such a long segment, but there's sort of a lot to go over. We have now covered pretty much every different form of calculating future value in a scenario where you have one amount of money that you're going to invest, and it's just a question of how you're going to invest it, how long, and at what rate, and what the compounding is. Now we're going to extend this to what happens if I'm going to make my investments over multiple years. And so we would call this a multi-period investment. So as an example, let's just consider an example where we're going to have $100 to invest today. We're going to have another $150 that we can put into the investment at the beginning of next year, and another $200 at the beginning of year 3. All those are going to be invested at 6% interest, and we're going to leave them in there until the end of year 10, which is 10 years from today. So the question is, how much money will you have at the end of year 10? What's the future value of this multi-period investment? Well, lucky for us, there's a way to break this down pretty easily. We can actually look at each of the 3 investments that we make and solve for what the value of each one will be at the end of 10 years, and then we just sum them up. So the first investment, the $100, it's going to be invested for 10 years at 6% because it's starting today. So 100 plus 106 times 2 raised to the 10th because it's 10 years. So 179.08. Now the second investment is only going to be invested for 9 years because we don't put it until the end of this year, the beginning of next year, and then it's going to sit till year 10. So there's only 9 years left. And so, excuse me, it only grows for 9 years, but it now has a value of $253.42. Again, you can solve that for yourself. The third $300 we're going to put in for 8 years at 6%. Sorry, I said that's 300. It's actually 200. My bad. And that's going to grow to $318.77. So each payment we've solved for the future value of those. If we add all of those up, then we would expect at the end of the 10 years to have $751.27 in that investment account. And that, my friends, is pretty much everything that I could imagine that you need to know at this point about future value. I know that we went through this rather fast. Part of the reason I did that, it is a video, so you can stop, kind of do your own thing. But I'm trying to keep this relatively short. We can discuss it further if you like. Thank you.